Okay, so babies are asleep. I have some time to record, and it looks like it's time for MATLAB at midnight. So, what are we going to do today? So, thus far what we've seen is we've seen ways to code up Taylor polynomials. We saw ways to code up interpolating functions using the van der Waals approach and also Newton's divided differences. That leaves one other kind of approximation that we've talked about so far, and that is the approximation method of Bernstein. So remember, Bernstein polynomials basically are applied to functions over 0, 1. Now you can always compress a function until it fits into the 0, 1 pattern, and then you can do the approximation and then stretch the approximation back out. And so that's more or less the approach that we're going to do. In any case, so what we're going to do today is we're just going to code up the Bernstein polynomials, and in a sense that's a little bit easier than doing the van der Waals matrix and doing the Newton's divided differences, because it isn't an interpolation problem. And so I guess I can keep jabbering, but why don't we just go ahead and get started. So let me go ahead and get a screen recording going, and yeah. Got a new fancy microphone here, so we're going to see how well that works. I'm still recording with my mic on my camera, which is actually a decent mic as well. But this one is made for like podcasting and things like that, and hopefully it'll be a little bit clearer than a little bit of noisiness that you would get between here and there. But we'll see. All right, so get that recording. Good. And boom, boom, and boom. Okay, so now that we're recording, let's go ahead. So I have this file here. I'm calling this Bernstein Polys.m, and so starting out with a comment of just Bernstein polynomials and approximations. I'm going to open up the van der Waals interpolation thing, and so we're going to approximate the same function that we did before. Looks like I still have this guy in there. Let's see. All right, there we go. So I like this one, and so I'm gonna say let's keep doing that guy. So this is a nice little function. Not gonna interpolate anymore. We're gonna approximate. So we're not matching the points that we're sampling from, but yeah. So the interpolation sites. Just gonna take a look at that. So. These aren't going to be interpolation sites anymore, but so we'll just call these samples of our function. So we're not interpolating, but we still need information coming from the function. So sample t and sample y. Right, and so these are all the things that we've made before in the past, and so nothing really complicated there. Okay, so let's go ahead and take a look and just do that whole plot thing again. Remember we were plotting from t going to 0 to 2 pi. So plotting code. And so we had that. And let's see. And then y was just this guy applied to that. And then we can go ahead and plot, right? So just pulling from old code, there's no need to rewrite that every single time. And ultimately we'll likely want to do this sort of thing too. And so I'll bring that over too. And with it comes its own plot. And so that was this one. So here. You know what? Here, I'm just going to copy all this over here. Because it'll be instructive to see the sites that we're using to approximate. So these are going to be sample t now and sample y. And so if I go ahead and comment this out and comment out this, and for now we're going to comment this, but we'll come back to this later. Okay, so let's go ahead and plot. Again, same function we keep looking at. These are our samples. They are evenly spaced, and that fits well for the Bernstein polynomials. And yeah, there we go. So let's see. I'm just curious to see how far sample t goes. It looks like it stops at just 6. And so that's going to be important for us later. So even though the approximation that we're plotting is up to 2 pi, it stops at 6 because that's the last 0.5 before it jumps over. And so we're going to have to be mindful of that when we're actually doing it. So I'm actually going to change this to just be 6, and let's see what ends up happening. Because we're going to have to rescale the whole interval, and so it's important for us to see where we're sampling, because we need to sample at both the 0, and we also need to sample at the right endpoint. And so here we want to make sure that those samples both make it in here. And so it looks like t at 0 and t at 6 are both in there, and that's good. And otherwise, yeah, we have all those points. Okay, so we need to figure out what the polynomial degree is. And this is going to be their samples minus 1, right? Because the polynomial, the number of free variables that you get for polynomial degree n is n plus 1, right? Because you not only have the term on x squared, x cubed up to xn, but you also have the constant term, and so it adds another layer. And so that tells you that if you have n plus 1 samples, then you need a polynomial of degree n. Okay, so this is going to be, let's call this degree poly is equal to the length of sample t. Okay, and so we're going to need to use that. All right, so if you remember, we have n. All right, so we need to make our basis functions. And so what we're going to need to do is we're going to need to make these guys. We need to make x to the k times 1 minus x to the n minus k, and then we need to multiply this guy by n choose k, right? Or that's n factorial divided by n minus k factorial times k factorial, right, on the bottom. And both of these need to be contained in there. Okay, so this is what we're going to be trying to make here. So these are the binomial coefficients, and these are my individual terms. Now we saw before that there's a slick trick, right? Like if you say I have 2 and you raise it to the power of say 0 up to say 5, then oops, if you put a period here instead, then it gives us 1, 2, 4, 8, 16, 32, right? So that's going to be where we're getting our x from, and so we're going to have so we're going to make a polynomial basis. So this is going to be polynomial basis, and this is going to be a vector of functions that we're going to have, and I'm going to try and make it a column vector, but we'll see how successful I am. I think it's really going to end up being a row vector, but that's fine. We can manipulate things to get what we need. So we're going to have as our polynomial basis, and this is going to be so it's going to be a function of x, and x is going accidentally hit the stop button. All right, so x is going to be raised to 0 up to the degree of our polynomial. Right? And this needs to be multiplied term by term with 1 minus x to basically the opposite. So I'm going to go this way. I'm going to say go from degree poly and increment -1 until you get to 0. So we're going to do that. Okay. And if you want to see what that'll give you, yeah, let's put this in, and I'll just put 2 here, and 1 minus 2 here, and oop, oh yeah, then just say degree poly is equal to 5, right? And so then if we go ahead and do that, oh, and I need to put a period there. Okay, there we go. So basically, we're going to be multiplying by -1 for each one of these terms. And we still keep those 2s that gave us like 1, 2, 4, 8, 16, 32. But here, since it's 1 minus 2, that's going to give us -1. And so it's going to give us -1 here, you know, et cetera, et cetera. So this is going to be -1 to the 5th, -1 to the 4th, -1 to the 3rd, -1 to the 2nd, -1 to the 1st, -1 to the 0th, right? And so, that's giving us that basis, so that's good. Now the last thing we need to do is look at the choose statements, and I don't know if I have anything. Hey, a YouTube channel. That's a really great YouTube channel. You also should subscribe. I hear that that math thing is all the rage these days. So let's go ahead and take a look at it's a MATLAB choose statements. Right. MATLAB choose and choose K. There you go. Always forget this one. Binomial coefficients. And MathWorks. Oh, it's actually that. And choose K. Okay, so let's give it a shot. So we're gonna have n choose K. So 3 choose 2 should be 3 factorial. 6 divided by 2 factorial times 1 factorial, so it should be 3, right? Good. Okay, that works. Now let's see what happens if I do 3, and I'll go 0 to 3. See if it gives me anything. Oh, no. Nope. Okay, so we're going to have to fill in a vector with this. So we're going to go 4, and then I'm going to multiply all this guys by that. So I need to multiply element-wise n choose k times these guys. So I'm going to say for I equals 1 up to degree of our polynomial, we're going to have, it's going to call this a. I'll have to make a, here, say a is equal to zeros of size 1 and degree poly plus 1. Okay, so filling this in, we're going to have n choose k of degree poly comma I, and yeah, is that right? Oh, okay, let's do this. I, and then, yeah, okay, so we need to start at 0 and go up to n, and so that's the rub there. So you can't start an index here at 0. MATLAB doesn't like that, so we need to start that index at 1, and so otherwise I could put I here. If I started the index at 0, I just had to put an I plus 1 there. Other way, it all works out. Okay, so now I take A and I dot multiply it, which means element-wise multiplication times that, and that should be our vector basis functions. Okay, so now we just need the weights. Now if you remember, the weights that would go on these polynomial bases is actually just the samples of our function. And so we already have sample y. If I, for instance, look at the length of sample y, we see it's 13, and sample t length, which is ultimately going to be the degree of the polynomial, is also 13. So they're in agreement. So then, if I take, let's see, what is sample y? It is a row vector. And so if I want to take all this, this is all a row vector, and I want to multiply it by another row vector, but I want the actual dot product. And I multiply it by y, sample y prime. And so this is going to be the f of 0 over so it's going to be the f of 0 over n, f of 1 over n, f of 2 over n, f of 3 over n, etc. until you get an f of n over n. And so that's going to be at, say, 1. But in this case, we've actually spanned the samples from 0 to 6. And so that sort of is a wrinkle in this, because this is only supposed to work up to that point. So we're going to have to do a little bit of finagling in order to make this work going from 0 to 6. And the way you do that is we're going to actually just divide each of these terms by 6. And so this is pretty close to the polynomial that we want. So I was going to leave this as a polynomial basis, and then we'll resize that as we need. And so the polynomial approximation at x is equal to our polynomial basis at x divided by the end point of our interval. And so here I'm just going to, since we don't have to do any shifting, I'm just going to rescale our values. And so this is going to be, see, we need the polynomial to start, the polynomial is made to start from 0 and end at 1. And so when we input 1 into, we put in 6 into this guy, we need to be putting 1 into here, right? So that should be divided by 6, pretty sure. And then we multiply by samples, by sample y prime to make this column vector. So it's a row times a column, that'll give us a scalar, and that's our final approximation at each point x. Okay, so that might take some finagling and practice, but as you keep playing with this code, it should become more obvious. Okay, so polynomial approximation is actually what we're approximating. And so if we come back to this plot code that was made for, it was made for the interpolation, we just put in polynomial approximation, and we can see how we did. Okay, now let's watch it all fall apart when I press play. All right, so remember this t should be going from 0 to 6, not 0 to 2 pi. And otherwise, we need to actually plot our polynomial. There we go. So let's push play, and there we go. Unrecognized function plot. Oh, I see. I accidentally uncommented a proper comment. Let's go ahead and do it. And something went wrong. Incorrect dimensions raising matrix to a power. This is in line 51, somewhere up here. Oh, that is not our code. But it said in our code this happened at point 32. All right, so polynomial approximation. Well, let's see what we get when we put in polynomial approximation 2. All right, so I can't even take a scalar. That's a problem. Is it a polynomial basis? Polynomial basis of 1. Yep, it's in there. Okay. So what is A? Okay, something went wrong. Oh, okay. This should have a period there. Okay. Now everything should run. Maybe not. All right. Okay, so let's see. Is a problem in polynomial basis. Polynomial basis at 1. What do we get? Okay, I got that. Ooh, let's see. Have fun. Oh, is it 2? Okay, cool. It's giving me stuff. I don't know why it gave me zeros. Oh, yeah, of course it gave me zeros all those ones, except for the one. All right, cool. All right. And it would have to give me all zeros except for at the one, because this would be 1 minus x, a 0 there. So that's good. All right, so the problem now it lies with this one. Let's see. Polynomial basis at x over 6. Let's try putting in, say, what, t1 into that. All right, that worked. Okay, and what is sample y? That a prime is a column. And so it should be a row vector times a column vector. Shouldn't be a problem. Let's see, what is size of polynomial basis at 1? 14. What is the size of sample y? 13. Well, there's our problem. So y is, what is the degree of the polynomial? What is the size? 13. Oh, right. I said it should be a samples minus 1. You guys might have even caught this, but I didn't implement that. All right, there we go. Okay, so now I think I caught all the problems, and we can run the code and see what we get. Okay, so this is our approximation, this little red line here. You'll notice that we have a whole bunch of samples, and we're nowhere near them. So our polynomial sampling approximation, it's sort of doing what our function does, but it doesn't hit those points exactly. And that's because this isn't an interpolation scheme. This is an approximation scheme. So that's not anything to worry about there. Do notice that we match here, and actually we did match at exactly one point in the middle, but that's probably more coincidence than anything. And I doubt that's actually matching. It's probably just very, very close. Okay, so now we have our first Bernstein polynomial approximation. This is with a polynomial of degree 13, and so we can go ahead and see if we can increase that. So let's take this down to 5. So now we've doubled the number of points. So this is now, the degree of the polynomial is now 24. And you'll notice that, again, on these big swooshes that we have here, the little polynomial isn't quite able to keep up with them. But at the same time, it is getting closer than it was before. So that's pretty positive there. And notice how quick that was. Compared to the Newton's divided difference method, which might have been my coding fault, this actually is working pretty quick. And it'll generally work faster than any interpolation scheme you come up with, because the interpolation scheme ultimately has to invert a 2x2 matrix. Basically, it has to invert the Van der Waals matrix in one way or the other. And in order to do that, that takes roughly big O of n cubed operations. It's actually big O of n squared plus a little bit, but you might as well think of it n cubed if you're naive in the construction of your algorithm. But the Bernstein polynomial approximation uses only the samples of the function and a basis that it always knows. And so this approximation scheme is actually going to be more like big O of n plus a little bit maybe. And so this will run dramatically faster. But it comes at a cost that your approximations really aren't nearly as close. So this is a polynomial of degree 24 that I'm showing you here. And this polynomial, if we use an interpolation scheme, would be practically matching this. And we almost matched with way less points last time. And so, so we require a lot more samples in order to get this approximation. It's not nearly as good, but the computation time is much better. So let's take us down to something dramatic, 0.1. Boom. And I ended up having a whole lot of problems. So we ended up hitting some sort of wall of integer arithmetic, floating point arithmetic in here. But we see we're actually still pretty close. Although now this is a polynomial degree 60, look at how many samples we have, and we're still not matching at these peaks. We're close. We're really close, but yeah, so it shows you that this approximation method is getting kind of poor, and these are all coming from rounding errors that we have. So we have maybe too many evaluation points, or too many sample points here that's actually leading to some sort of confusion when we're trying to implement this. So we can try this. I'm just going to try something stupid. Put 0.01, and it's going to be like a polynomial degree like 600 or something. And okay, finally we seem to be matching. You can't even see with among all these density sample points. But yeah, this is a degree of polynomial 600. Let me see if I just zoom in here so you can see what's going on. Boop. All right, so we're still not quite matching, but you know that's pretty damn close. So these points here, it looks geometric because truly MATLAB actually does piecewise linear interpolations of points that you give it, but that's neither here nor there. But yeah, so this gap here is so a little bit over the 0.74, and this one's a little bit under the 0.6, and so it's within 0.02 of each other. So you know that's pretty decent. I've seen better approximations, but you know, in a pinch, if you just need something real quick, this works fast. I mean, if I try to do a polynomial of degree 600 in the other cases, it would not have worked out nearly as nicely. Now it's just, there we go back. But okay, so that's a pretty good approximation, and yeah, I think that might just be a good point to stop. There's not much else that we could really do that would shake up this problem. I mean, we saw already that it has a little bit of trouble approximating something that is already a power series in analytic, so it should work out really well there. Most approximation problems do work out well, but here we saw it had a little bit of trouble converging to it. Like, these are infinitely differentiable, super smooth and everything. These are like the ideal functions that you'd want to approximate, because you should get fairly fast approximation. But we saw that we really didn't, not with the Bernstein polynomials. But this is a lot easier to code than the other ones, and at the end of the day, it runs a lot faster. And so it just depends on what sort of accuracy you demand out of your approximation that you might want to use this, especially if you're using like a really small processor or something like that on a small local machine. It might not have the power to do a quick conversion, especially if you're trying to do something in runtime. And so so this might be the best bet you have as far as doing an approximation and extrapolation sort of problems. But yeah, okay, I'll stop babbling, and yeah, we'll just call it here. All right, thanks for watching. Bye.